right, a question was brought up in the break time here about this. The phase plane in Mathematica has subtleties in the way it looks that we did not have when we drew it by hand. For example, the fact that the solution curve looks almost horizontal down here. It's not exactly horizontal again. It is moving slightly to the south, down. Whereas when I draw it on the board over here, I draw the southward motion more pronounced, in a more pronounced way. That's okay, okay? If you don't have a computer output to look at, and you draw something like this, it's good enough, right? If you do have a computer output to look at, then you can draw more accurate looking solution curves. And if you started down here, for example, your solution curve could look more horizontal.
Are they crossing like horizontally and vertically, or at like 90-degree angles to the nullclines?
They're crossing the blue line horizontally.
Okay. So it doesn't
And
matter
when a solution crosses the red line, it crosses it vertically.
It doesn't matter like what angle or where the line is at, just that it's crossing.
Right, right. If we had an initial condition over here, the solution would probably look like this. It would probably look pretty horizontal for a while. And then when it gets close to the red line, which it has to cross vertically, all of a sudden probably it would shoot up and come in this way. That's a typical kind of thing that would happen. Okay, so it's kind of subtle in that way. You really need the computer output to be confident in that. This more generic kind of picture, which is not as accurate probably, yeah, I know is not as accurate, is good enough for us. By the way, there is one solution curve that approaches the origin as t goes to minus infinity, and approaches this point as t goes to plus infinity, but never enters this region or that region. It might look like it goes straight toward that point, although it's not necessarily straight. But it might look straight. That's a special kind of solution. It's not going into either of these regions. And sometimes in other situations, those special solutions are pretty important, actually, to help you finish the picture. But that's kind of a subtlety that I wouldn't expect you to know. All right. In lecture B, our main task now is to look at something called the pendulum. It's going to be our last model. And we'll do it without friction. Although maybe if I have time briefly on Friday before we review, maybe I'll look at what it looks like with friction. Though I probably won't spend more than about a minute on it. We'll just look at some graphs. So what is a pendulum? Again, it's a bob that's swinging back and forth on some stiff rod of length, call it capital L here. It's attached to some wall or something, and we are allowing it to be free to go up and over if it needs to, if it's got enough initial velocities. And there's no ceiling it's going to hit necessarily. It's got a bob at the end of it, of mass m. We assume the rod is stiff, but mass negligible, okay? Which could get you into trouble with this around the horn kind of thing. Like, if its mass is negligible, is it really stiff? Okay? You might worry about that kind of thing, but as an initial approximation, we don't worry about it, okay? The mass is constrained to move around some circle. Centered where it's attached to the wall, circle of radius capital F. The only force on the mass is the downward force due to gravity, whose length would be mg. And as a vector, you could say, if the upward direction is positive, You could write this as negative mg times j hat, where j hat is the unit vector pointing straight upward as a vector. You could write it as negative mg times j hat. But we're not going to bother with that. That's just, the length is m times g, where g is, again, the acceleration due to gravity. What we're interested in actually here is how the angle changes over time. That's what we're interested in. How does the angle change over time? Because the angle completely determines the motion. Let's call this length right here, let's call that S. Let's draw some other triangles in here. The component of the force of gravity in the direction tangent to the circle here would look about like this. And the length of that arrow is essentially the magnitude of the force that the bob feels, so to speak. It's the effective force because it's constrained motion along the circle. If this angle is theta, then actually this angle is going to be theta. Why? Because if you continue this line this way, this angle would be theta, because you've got two vertical lines and the same line. And then these lines are parallel, and you've got alternate interior angles are congruent. That angle is theta 2. Also, I should say. That's a right angle. Mm-hmm.
So are the two thetas, are those different values?
No, they're the same value.
Okay.
All these angles have the same value. They all can be labeled with a theta. We've got a right triangle in there, and then using trigonometry, SOHCAHTOA, the length of that side, which is the important length to focus on, is mg sine theta. The sine of this angle in this right triangle is going to be opposite over hypotenuse. So the sine of the angle is the length of this side divided by the length of that side. If you solve for the length of this side, then by multiplying both sides by the length of that side, look at that. Okay, I did verbally what maybe you want to write down some equations to see that more clearly. The sine of this angle is this side divided by that side, solved for that side. And so essentially, this is the magnitude of the force on the bob with respect to moving along the circle. S equals L times theta. The velocity of the bob is ds dt is L times d theta dt. And the acceleration of the bob, the second derivative of s with respect to time, is L times the second derivative of theta with respect to time. L is constant. And so now Newton's second law, N2 stands for Newton's second law. F equals ma says the mass times this will equal this with a negative sign because the force is in the opposite direction. M times the second derivative of s with respect to time will equal negative mg sine theta. Or we want to get things in terms of theta. Plug L times the second derivative of theta with respect to t into here. You can cancel the m's. You can also divide both sides by L. You can write that the second derivative of theta with respect to time is negative g over L sine theta.
Wait, I have a question. So where do we get the L from?
L is the length of the rod. It's a stiff rod, so L doesn't change. It turns out the length here along the arc length, is called S. That is the same as L times theta when theta is in radians. That's a fact. If I differentiate these both sides with respect to t, I get this because L is constant. This is mass times the acceleration. This is the force, and it's in the opposite direction. Then what I did was I replaced this, I canceled the m's. I replaced this second derivative, e squared s t squared, with that.
Oh.
Then I divided both sides by L.
Ah. Okay.
Okay?
Yeah, now I see it.
To get that equation. Just for the sake of keeping things simple, let's let L equal 1. I guess that would be meter. A 1 meter long rod, just to keep things simple. And your equation then becomes the second derivative of theta with respect to time is negative g sine theta. I'm not going to bother replacing g with 9.8. I'll just leave it as g. That's a second order differential equation. Just like we had a second order differential equation for a mass on a spring. However, it is a more complicated equation because it's what's called nonlinear. With the mass on a spring, we had the second derivative of x with respect to time was something times negative theta. Negative x, excuse me. We don't have something times negative theta here. We have something times sine of theta, negative sine theta, not theta. The sine theta is the nonlinearity. Nonlinear. Although, by linear approximations, sine of theta is approximately theta when theta is small. And because of that, this does act like a harmonic oscillator when the oscillation is small. You can use sines and cosines pretty accurately to model the back and forth motion of a pendulum, a bob on a pendulum, when the angle is small. It's when the angle gets big that using a sine and a cosine is not very accurate, because you get a significant slowing down near the peak, especially if it's an oscillation that comes close to the peak. Like that. And sines and cosines don't work so well anymore. In fact, we need to use NDSolveValue if we're going to have any hope of graphing solutions of this instead of just DSolveValue. The n needs to be in front of it. We need numerical approximations. Just like before, though, we can write this as a system. We can consider v to be d theta dt, although that's an angular velocity, not an actual velocity. An angular velocity would be in radians per second, whereas an actual velocity would be in meters per second. Angular velocity. I'll call it v anyway. And that definition becomes one equation in the corresponding system. The first equation, d theta dt equals v, and dv dt equals, well, it's, dv dt is the second derivative of theta with respect to t, it equals negative g sine theta. So this is our first order system. This is a second order scalar equation, single equation. This is a first order system that's equivalent to the second order equation. Since it's now a first order system, we can now draw a phase plane. Let's see how far we can get drawing a phase plane by hand. And then we'll use Mathematica. This is going to be a theta v plane. Theta being the angular position, so to speak, of the pendulum, v being the angular velocity. Look at these equations. d theta dt is equal to 0 when v is 0. The theta nullcline is when v is 0, That's the theta axis. d theta dt is 0 when v is 0, when you are on the theta axis, which is the horizontal axis. Therefore, the horizontal axis is the theta nullcline here. You got to cross that vertically. The theta axis, where v is 0, that is the theta nullcline. Theta dt is 0. What about the v nullcline, where dv dt is 0? That's going to occur when sine of theta is 0, which has infinitely many different values that theta could be to make it 0. 0, pi, 2 pi, 3 pi, 4 pi, negative pi, negative 2 pi, negative 3 pi, etc. Theta equals 0 is one of them, but also at pi, at 2 pi, at 3 pi, etc. Negative pi, negative 2 pi, negative 3 pi, etc. Ignore the inaccuracies in the picture. Where red and green cross, you've got equilibrium points. There's infinitely many equilibrium points. Now that said, in the physical reality of the situation, there are only two effective equilibrium points. The pendulum points straight down, the pendulum points straight up. And the rod is stiff, so it doesn't get crunched or something. It's massless, but it's strong enough to hold the pendulum straight up if you could get it exactly straight up. But why is the phase plane showing infinitely many? It's because angle measure is an ambiguous thing, right? An angle of 0 is the same as an angle of 2 pi, is the same as an angle of 4 pi, as far as where you are. That's why you're getting infinitely many points in the phase plane that are equilibrium points. What this actually means, and maybe I'll highlight this briefly on Friday with just a picture to show you, is that the true phase space of the situation is actually not a plane, it's a cylinder, where the angular variable goes around the cylinder, and the velocity, the angular velocity vector variable goes up and down the cylinder. That's the true phase space of this. What about directions of motion of the solution curve? dt is going to be positive when v is positive, when you're above the theta axis. So it's all rightward pointing arrows up here, and the theta dt is negative when you're below the v-axis, when v is negative. All leftward pointing arrows down there. What about, where is dv dt positive and negative? It's going to be positive, think about this, you got a negative sign there, when sine of theta is negative. dv dt will be positive. For example, sine of theta is negative. If you think about the graph of sine of theta, an ordinary graph, sine of theta looks like this. Sine of theta will be negative, for example, between negative pi and 0. dv dt will be positive for such values of theta. When theta is between 0 and pi, sine of theta is positive. You got the negative sign there, so dv dt is negative. And the up-down nature of these arrows will change, oscillate. Up here, down here, up here, down here. Over here, we're going to have down and up there and there, down and up there and there. So the vectors in the vector field now for the phase plane will go northeast, southeast, northeast, southeast, northeast, southeast up there, and then northwest, southwest, northwest, southwest, northwest, southwest down there. Now try to draw in solution curves. For example, if your initial condition is close to 0, 0, you got to go southeast, you're going to have to cross the theta axis with the vertical tangent, Before heading southwest now and cross the v-axis with a horizontal tangent. I didn't make those horizontal tangents, by the way. Etc. I'll stop there. Now you're going to head to the northwest before crossing vertically, then the northeast. Is this going to be a periodic solution? Should be if there's no friction, right? It's going to oscillate forever, going around like that. And that is similar to what a parametric curve involving sine and cosine would look like for a mass of a spring. However, if we pick an initial condition close to this point there, theta is pi, v is 0, we are close to straight up. Theta is close to pi. We give it, it's giving a little kick toward theta equals pi here. So this is going to move rightward initially. It's got to cross the red axis, the theta axis vertically, before heading down this way. It's got to be periodic. The motion is going to be something like this. Maybe I should have started on the theta axis for the velocity 0. It does have to be periodic. It hopefully makes a little sense based on the picture that the curve itself will not be circular, but will probably be an oval. I mean, you might guess it's circular, but if you did, you'd be wrong. More like an oval. Is that oval an ellipse? I think not, actually. I'm pretty sure not. And moreover, another subtlety of the solution curve along this oval is that it moves slower near that equilibrium point in that one and a lot faster here and here. The motion is pretty slow at first, and speeds up and slows down. Speeds up and slows down. And if you graph theta and v versus t for this kind of initial condition, you definitely will see they look like sines and cosines. Let's end class by using Mathematica to analyze this now. All right, so let's call them f of theta comma v is the right-hand side of the d theta dt equation, and that was just v. And g of theta comma v is the right-hand side of the v dt equation, and I probably shouldn't call it g, huh? Okay, I'll put a negative 9.8 in here. I'll go ahead and use the gravitation constant in standard units. Let's go ahead and right away use NDSolveValue. Theta sol, by the fact that I'm calling this theta sol is just using a different letter, a different variable name, and sol just stands for solution. I could use something else. I'm going to need to use NDSolveValue. Theta prime of t equals f of theta of t, v of t, v prime of t equals g of theta of t, comma v of t. Let's pick an initial condition close to the straight up position. So theta of 0 is close to 2 pi. How about, in fact, theta of 0 is 3.14. By the way, if you ever become a teacher, there are lots of even college students who think pi equals 3.14. No, it doesn't. But they like have 3.14 so much in their brains that they think it does. I made that mistake of assuming everybody knew it wasn't actually equal to pi once when I was teaching a pre-calc course, and I learned my lesson. That's not necessarily something everybody knows. How big should t go? I don't know. Maybe 0 to 10 plays it safe enough. I'll try it. It's already giving us these pre-graphs. They don't look exactly like sines and cosines, do they? Let's go out to double that. They are periodic. But they're definitely not sines and cosines. Theta of t, I think, is the blue one here. It's close to, yeah, it's close to pi to begin with. It stays close to pi for about 2 seconds before rapidly going down to close to negative pi. Stays close to negative pi for a while before rapidly going back up close to positive pi. The velocity, the orangish one, is the derivative of theta. It's giving the slope. The slope is close to 0 but negative. Maximum negative slope right about there, where you're going through the bottom position. Slope, the angular velocity comes back close to 0. Hang with me here, a couple more important things to say. I can do a parametric plot of this in a phased plane. I'm not going to bother drawing the vector field. However, I'm going to draw something else. Yeah, it doesn't look like an oval. It's somewhat ovular, would that be a word? But it's definitely not an oval. Oh, that didn't do it, sorry. Let me put one more thing on this picture. ContourPlot I'm going to plot a contour map which includes colors, like I showed you the other day, of a function of 2 variables. And the function of 2 variables is going to be v squared over 2. Seems like that would be kinetic energy if the mass was 1 of these. Minus 9.8 cosine theta. Is that potential energy? Theta goes from negative 10 to 10. V goes from negative 10 to 10. Let's put a lot of contours in here. Kind of hard to see there. Those are the level curves of this function of 2 variables there, where that function of 2 variables is constant. See the different constants? And that function of 2 variables, if the mass is 1 kilogram, is the potential energy, or excuse me, kinetic energy plus potential energy, total energy for the system. Look at the solution curve. It's on top of one of those level curves. Total energy is constant, it's conserved, is what that means. What is the total energy of this particular pendulum? About close to 11 joules, I guess. You might wonder, well, how there can be a minus sign with potential energy. That's a little confusing too, to me. Potential energy can sort of go up and down by a constant, so I'm not sure that I can explain it beyond that. But the point here is total energy is conserved. We don't have any friction. Total energy is conserved. This function right here, by the way, has a name. It's called a Hamiltonian function, and this is called a Hamiltonian system. I will briefly re-emphasize these things also on Friday. See that.